So, here's something worth thinking about as you settle in tonight. Right now, in the room where you are lying, something extraordinary is happening. Energy is moving, enormous amounts of it. It is passing through the walls, through the air, through the blanket draped over you, through the skin of your hands and the bones beneath them. Light from your screen is arriving at your eyes. Sound from my voice, if you have a speaker on, is pressing gently against your eardrums. The Wi-Fi signal carrying this audio is rippling through the space around you in waves that pass through furniture and plaster and glass as though those things were barely there. If there is a window nearby, infrared radiation from every warm object outside is streaming through it.
And beneath all of that, beneath every signal and shimmer and hum, hundreds of trillions of neutrinos from the core of the sun are passing silently through your entire body every single second. And not one of them will ever touch a single atom inside you. All of this is happening simultaneously, right now, in the space between your pillow and the ceiling. And every single one of these things, the light, the sound, the heat, the Wi-Fi, the neutrinos, every one of them is a wave. But here is the part that should genuinely stop you for a moment. None of them are carrying anything with them. The sound of my voice reaches your ear, but the air in this room has not traveled from wherever I recorded this. The light from your screen arrives at your retina, but nothing, no substance, no particle of matter has crossed the gap. The Wi-Fi signal passes through your wall, but your wall has not moved. Energy is arriving at your body from all directions, continuously, relentlessly, and yet nothing is being delivered. No package, no parcel, no substance crossing the distance. The energy just appears, as if the universe has figured out a way to send a message without sending a messenger. How is that possible? How can something move from one place to another without anything actually making the trip? That question, that strange, quiet, almost unsettling question, is what we are going to sit with tonight. Because it turns out that the answer to it is one of the deepest ideas in all of physics. And it does not require equations or laboratories or expensive instruments to understand. It requires patience and a willingness to let something familiar become strange again. You have lived with waves your entire life. You have watched them on water. You have heard them in music. You have felt them in the rumble of thunder through your chest.
You may have noticed that when a wave rolls across a lake, the water itself does not travel with it. A duck sitting on the surface bobs up and down as the wave passes beneath, but the duck does not ride the wave to the far shore. The wave moves, but the duck stays. And you may have accepted that fact as a simple curiosity, something interesting but not particularly mysterious. But tonight, I want you to hold that image a little longer. Because inside that simple observation is a question that haunted some of the greatest physicists who ever lived. And the answers they found reshaped everything we know about light, about sound, about matter, and about the nature of reality itself. So, as you lie there, here are the questions that this journey will try to answer, slowly, gently, one at a time. When you speak, your voice reaches someone across the room, but the air between you and that person has not traveled anywhere. The air stayed where it was. So what actually crossed the gap? What left your mouth and arrived at their ear, if it was not air? Right now, light from your screen is warming your face, just slightly. That light traveled from a source to your skin, and it delivered energy, real, measurable energy, enough to trigger chemical reactions in your retina. But nothing, no particle, no substance, no material of any kind made the trip. If nothing was delivered, how is the energy arriving? And then there are the words that physicists use to describe waves. Frequency, wavelength, amplitude, phase. You have probably heard them before. But what do they mean for you, practically? Why does a foghorn sound completely different from a whistle, and what does that difference tell you about the wave arriving at your ear? Why does the bass from a speaker reach you in the next room, but the singer's voice does not? Something about the wave is changing, and those 4 words are how we describe what changes. And finally, what happens when 2 waves arrive at the same point in your ear at the same time? Because this is happening constantly. Every sound you hear is a combination of waves from multiple sources, all overlapping, all arriving at your eardrum simultaneously. Sometimes they build each other up. Sometimes they tear each other apart. 2 speakers playing the same note can, if you stand in exactly the right spot, produce complete silence. 2 beams of light can produce darkness. How is that possible? And why does it explain the reason you can hear someone calling your name from around a corner, even though you cannot see them? The reason the sky above you is blue? The reason a CD shimmers with rainbows when you tilt it in the light? All of this from a question that starts with a duck on a lake. The pattern moves, the water stays. What then is actually moving? Let's find out. And let's take our time doing it. Everything begins with something out of place.
A leaf lands on a still pond. A finger plucks a guitar string. Someone claps their hands in a quiet room. Before any of these things happen, there is a kind of equilibrium, a balance, a settled state where everything is resting comfortably where it wants to be. The surface of the pond is flat. The guitar string hangs in a gentle curve. The air in the room is still. And then something disturbs that balance. Something pushes or pulls or drops or strikes. And for the briefest moment, the world is no longer where it wants to be. This is the beginning of every wave that has ever existed. A disturbance, a nudge, something taken out of its resting position. And what happens next is so simple, so quietly inevitable that you could almost miss it. But it is the seed from which every wave in the universe grows. Let's watch it happen, slowly, on the surface of a pond. Because water is one of the most forgiving teachers in physics. Imagine a perfectly calm pond on a windless evening. The surface is so still that it reflects the sky above like a mirror. And then a single raindrop falls. It strikes the surface and pushes a small circle of water downward. That water, the water directly beneath the point of impact, has been displaced. It has been forced below where it naturally wants to sit. And the moment it is pushed down, something begins to push it back up. Gravity, mostly, pulling on the surrounding water, and the surface tension of the water itself. That thin, elastic film that holds the surface together. Both of these forces are now working to restore the balance that was broken. They want the surface flat again. They want that small depression to fill in, to rise, to return to where it was. And this is where things get interesting. Because the water does not simply rise back to its original level. and stop. It overshoots.
The forces pulling it back are strong enough to carry it past the resting point, past the flat surface, and up into a small crest. A tiny hill of water that was not there a moment ago. Now the water is too high instead of too low, and the same forces that pulled it upward when it was in the dip now push it back down. Gravity pulls the crest downward. Surface tension smooths the bump, and the water drops below the resting point again, though not as far as before, and rises again, though not as high. Back and forth, up and down, in a quiet, patient, diminishing oscillation. This is what physicists call a restoring force at work, and the result is oscillation. The water overshoots its target, corrects, overshoots again, corrects again, in a rhythm that is as old as physics itself. You see the same pattern everywhere. A child on a swing is pulled back by gravity past the lowest point, rises on the other side, returns. A spring with a weight attached stretches too far, snaps back past its resting length, compresses, returns. A tuning fork struck against a table bends one way, then the other, then back, vibrating hundreds of times per second. In every case, the story is the same. Something is pushed away from where it wants to be. The universe tries to put it back, and in trying, it pushes it too far in the other direction. This overshoot, this gentle failure to land perfectly on the mark, is the heartbeat of oscillation. Without it, there would be no waves. Without it, there would be no sound, no light, no music, no color. The universe's inability to restore balance perfectly on the first try is, in a sense, the origin of nearly everything you have ever experienced. But so far, we have only described something going up and down in one place, a single point on the surface of the pond, bouncing. That by itself is an oscillation, a vibration, a local disturbance. Where does the wave come in? Where does the traveling begin? Here is where the magic happens. And I use the word magic carefully, because once you see this mechanism clearly, it stops feeling like magic and starts feeling like the most natural thing in the world. But the first time you really understand it, there is a moment of quiet wonder that is hard to forget. When that small patch of water at the impact point rises into a crest, it does not rise alone. It pushes on the water immediately surrounding it. The water just to its left and just to its right, and in every direction around it, gets nudged upward slightly. And those neighboring patches of water, having been lifted slightly above their resting positions, now experience the same restoring forces. They are pulled back down. They overshoot. They rise. They push on their neighbors, and those neighbors push on theirs. The disturbance is spreading, not because any water is traveling outward, but because each tiny piece of water is doing exactly what the first piece did, oscillating up and down around its resting point, and in the process, nudging the next piece into doing the same thing. The motion is being passed along, neighbor to neighbor, in a chain that extends outward from the point of impact, in an expanding circle. And this, precisely this, is a wave. The pattern of oscillation moves outward. The water itself stays where it is. Each molecule of water simply rises and falls in its own small patch, doing its own small part. And the result is a ripple that travels smoothly across the entire pond. The ripple is not a thing. It is not made of any particular water. It is a pattern, a shape, a coordinated behavior that propagates through the water without requiring any of the water to follow it. Think about that for a moment.
If you were watching from above, you would see the circular ripple expanding outward, growing larger, reaching the edges of the pond. It looks like something is moving. Your eyes track it as a thing, an object, a ring of raised water gliding across the surface.
But if you could somehow tag individual water molecules and follow their paths, you would see that each one merely wobbles in a tiny circle or an oval and returns very nearly to where it started. The wave passed through them. They did not go with it. There is a beautiful way to picture this. Imagine a long line of people standing in a row, shoulder to shoulder, in a field. The first person leans gently to the right, nudging the second person. The second person, pushed slightly off balance, leans into the third. The third leans into the fourth. The lean passes down the line. If you watch from a helicopter above, you would see a visible ripple of motion traveling from one end of the line to the other.
It would look like a wave. And yet, every single person stays in their spot. Nobody walks forward. Nobody changes position. Each person merely leans slightly, then straightens back up. The lean travels. The people do not. Waves are, at their heart, an act of cooperation. Each tiny participant does something very small, very local, very brief. And the sum of all those tiny local actions becomes something that travels vast distances. A ripple on a pond can reach the far bank. A sound wave can cross a concert hall. A light wave from a distant star can travel for 100 million years across the emptiness of space and still arrive with enough energy to land on the back of your retina and create the sensation of a pinprick of light in the night sky. And in none of these cases does any material make the journey. The energy makes the journey. The pattern makes the journey. The material stays home. This is the central strangeness of waves, and we are going to carry it with us through every chapter that follows. Because every time you think you understand it, every time you think you have made peace with the idea, we are going to look at a new kind of wave, in a new kind of medium, and the paradox is going to deepen. Sound waves will push the idea further than water waves. Light waves will push it further still. And by the end of this journey, we will arrive at a place where the question, what is actually moving, becomes so profound that it touches the very foundations of what we mean by reality. But before we move on, there is something worth lingering over. Because the picture of the wave on the pond hides a detail that is easy to miss, and that detail will become important later. When you watch a ripple travel across the surface of a pond, the water is not simply going straight up and down.
If you could track a single molecule of water as the wave passes, you would see it moving in a small circle. As the crest approaches, the molecule moves upward and slightly forward, in the direction the wave is traveling. At the top of the crest, it is moving mostly forward. As the crest passes, the molecule moves downward and slightly backward. At the bottom of the trough, it is moving mostly backward. And then it loops around again, rising forward, falling backward, tracing out a small circular orbit once for each wave cycle. The molecule ends up very close to where it started, having drawn a little loop in the water, contributing its tiny circular motion to the forward march of the wave. These orbital motions are not confined to the surface. They extend downward into the water, growing smaller and smaller with depth. At the surface, the orbits might be a few centimeters in diameter. A meter down, they are noticeably smaller. A few meters down, they are barely perceptible.
And below a certain depth, which depends on the wavelength, the water is essentially undisturbed. The wave is a surface phenomenon, a thin layer of organized circular motion on top of a vast, still body of water. This is why submarines dive during storms. Below a certain depth, the ocean is calm regardless of what is happening at the surface. The towering waves that can batter ships and capsize boats are confined to the upper layer, a few tens of meters at most. Below that, the circular orbits of the water molecules have shrunk to nothing, and the sea is quiet. The wave's influence decays exponentially with depth, fading with a characteristic scale that is roughly equal to the wavelength divided by 2 pi. For a storm wave with a wavelength of 100 meters, the motion is negligible below about 15 or 20 meters. The raging surface is separated from the silent deep by nothing more than the physics of circular orbits diminishing with depth. And here is a lovely consequence.
The speed of a deep water wave depends on its wavelength. Longer waves travel faster than shorter ones. This is something you might not expect, because in many other contexts, waves of different wavelengths all travel at the same speed, like sound waves in air, where bass notes and treble notes arrive at your ear simultaneously. But water waves do not work this way. In deep water, a wave with a wavelength of 100 meters travels about 12.5 meters per second. A wave with a wavelength of 400 meters travels about 25 meters per second, twice as fast. The speed is proportional to the square root of the wavelength. This has a beautiful consequence for ocean storms. When a storm generates waves far out at sea, it creates a chaotic mixture of wavelengths, a jumbled mess of short, choppy waves and long, rolling ones, all tangled together. But as this mess travels away from the storm, the longer waves outrun the shorter ones. The long waves pull ahead, stretching away from the storm in clean, organized lines. The short waves lag behind and gradually lose their energy to friction and turbulence. By the time the waves reach a distant shore, hundreds or thousands of kilometers from the storm, they have sorted themselves by wavelength. The long, gentle swells arrive first, smooth and evenly spaced, carrying the memory of a storm that may have already dissipated. Days later, shorter waves may arrive from the same storm, with a different character, choppier and less organized. The ocean is performing a kind of natural sorting, separating waves by wavelength through nothing more than the difference in their speeds. Surfers know this well. A good swell, the kind that produces clean, rideable waves, is a swell that has travelled a long distance and has had time to sort itself. The long waves arrive with a regularity and a smoothness that short-distance wind chop never achieves.
There is a patience in these waves, a quality of having been refined by thousands of kilometers of open ocean, each kilometer filtering out a little more of the chaos and leaving behind a little more of the order. It is one of the most vivid demonstrations in nature of how time and distance can transform disorder into something beautiful and rhythmic. This dependence of speed on wavelength is called dispersion, and it is important enough to deserve our attention for a moment, because it appears in many other contexts beyond ocean waves. In optics, the speed of light in glass depends slightly on the wavelength. Red light travels a tiny bit faster through glass than blue light. When white light, which contains all colors, enters a glass prism, this difference in speed causes the colors to separate, each bending by a slightly different angle, fanning out into the familiar rainbow spectrum. Isaac Newton demonstrated this in 1666, showing that white light is a mixture of all the colors of the visible spectrum, separable by their different speeds in glass. The rainbow you see after a rainstorm is produced by the same mechanism, each raindrop acting as a tiny prism, separating the sunlight into its component wavelengths. Dispersion will come back when we talk about diffraction, because the way waves spread when they pass through openings depends on their wavelength. Different wavelengths spread by different amounts, And this differential spreading is what produces some of the most striking diffraction patterns in nature. But for now, let us return to our main thread, the paradox of motion without motion, and move forward. But before any of that, we need to learn the language, because waves have a shape, and that shape can be described with extraordinary precision using just a handful of words. Words like amplitude, wavelength, frequency, period.
These are not just vocabulary. They are the keys to understanding everything that waves do, every behavior they exhibit, every phenomenon they create. And the remarkable thing is that once you understand these 4 words, truly understand them, you can explain why a foghorn sounds different from a whistle, why the ocean is blue, why your microwave heats food, and why 2 speakers playing the same note can, in certain positions, produce complete silence. 4 words, an entire universe of behavior. That is where we are headed next. We asked at the beginning, why does a foghorn sound different from a whistle? What is actually different about the waves arriving at your ear? The answer lies in the shape of the wave, and that shape can be described with just a few words. So let's learn them. If you could freeze a wave in time, stop it mid-motion, and look at its shape, you would see something immediately familiar. You would see a curve. A smooth, rolling, up and down curve that rises to peaks and dips into valleys with a kind of mathematical regularity that feels almost too clean, too perfect to be natural. And yet it is entirely natural. This shape, the sine wave, appears whenever a restoring force pulls something back toward balance in proportion to how far away it has been pushed. Which is to say, it appears almost everywhere. The shape of a wave frozen in time looks like a landscape. There are hills, and between them there are valleys, and between those valleys there are more hills, stretching on and on in a repeating pattern. The hills are called crests, the valleys are called troughs, and the flat line in the middle, the line that runs through the center of the wave, halfway between the highest point and the lowest, is the resting position, the level at which the medium would sit if there were no wave at all. Let's start with the simplest question. How tall is the wave?
If you measure from that central resting line to the very top of a crest, you get a number. That number is the amplitude of the wave. And amplitude tells you something very specific, something very physical. It tells you how far the medium has been displaced from where it wants to be. A wave with a large amplitude has pushed the water, or the air, or whatever it is traveling through, a long way from its comfortable resting position. A wave with a small amplitude has barely disturbed anything. You can feel the difference between high amplitude and low amplitude every day of your life. When someone whispers, the air molecules near your ear are barely shifting. The pressure changes arriving at your eardrum are tiny. The amplitude is small. When someone shouts, those same air molecules are being shoved much farther from their resting positions. The pressure swings are large, the amplitude is large, and your ear registers that difference as loudness.
A loud sound is, quite literally, a wave with a bigger amplitude.
The air is being pushed harder. The same is true of waves on water. A gentle ripple has a small amplitude. A towering ocean swell, the kind that lifts a ship and then lowers it again, has an enormous amplitude. In both cases, the wave is doing the same fundamental thing, passing a pattern of displacement through the water. The only difference is how much the water has been displaced. And here is something worth knowing, something that will come back to us later when we talk about energy. The energy carried by a wave does not increase in a simple, proportional way with the amplitude. It increases with the square of the amplitude. If you double the amplitude, the energy does not double, it quadruples. If you triple the amplitude, the energy goes up by a factor of 9.
This is why a shout carries so much more energy than a whisper, and why a tsunami, which may have only a modestly large amplitude in deep water, releases catastrophic energy when it reaches shore, and all of that amplitude is compressed into a shallow space. The relationship between amplitude and energy is one of the most important in all of wave physics, and it hides in plain sight every time you turn up the volume on a speaker. Now, let's look at the wave from a different angle. Instead of asking how tall it is, let's ask how long it is, or more precisely, how long is one complete cycle of the wave. Imagine you are standing at a crest, the very top of one of those hills in the wave's landscape. If you walk forward along the wave, you will descend into a trough, climb back up to the next crest, and arrive at a point that looks exactly like the one you started from. The wave is repeating itself. The distance you walked from one crest to the identical next crest is the wavelength.
It is usually written with the Greek letter lambda, and it is measured in meters or centimeters or nanometers, depending on the kind of wave you are dealing with. Wavelength tells you the spatial scale of the wave, how spread out each cycle is. A wave with a long wavelength has wide, gentle undulations. The crests are far apart. The rises and falls happen over large distances. A wave with a short wavelength is compact and tight. The crests are close together. The pattern repeats rapidly over a short distance. You can see the difference by comparing the gentle roll of ocean swells to the rapid chop of small, wind-driven waves near the shore. The swells have long wavelengths, sometimes 100 meters or more from crest to crest. The chop has short wavelengths, maybe a meter or two. Both are waves. Both are patterns of displacement traveling through water. They differ primarily in how much space each cycle occupies.
And now we arrive at one of the most important words in all of wave physics, and perhaps the one that is most often misunderstood: frequency. Frequency does not describe the shape of the wave in space, it describes the shape of the wave in time. Specifically, it answers the question, if you stood in one spot and let the wave pass through you, how many complete cycles would go by in 1 second? Imagine you are standing waist-deep in the ocean, and a series of waves is rolling past you. Each wave lifts you up to a crest, and then lowers you into a trough. If you count how many times you are lifted to a crest in 1 second, that count is the frequency of the wave. If 3 crests pass you in 1 second, the frequency is 3 cycles per second. If 50 crests pass you, the frequency is 50 cycles per second. The unit is called the Hertz, named after Heinrich Hertz, and 1 Hertz simply means 1 complete cycle per second.
Frequency is what your ears interpret as pitch when you listen to sound. A sound wave that cycles very quickly, hundreds or thousands of times per second, sounds high-pitched. A flute playing a high note produces sound waves with a frequency around 2000 Hertz, meaning the air near your ear is being compressed and released 2000 times every second. A bass drum produces sound waves with a frequency of perhaps 50 or 60 Hertz. The compressions arrive much more slowly, much more ponderously, and your brain interprets that slow cycling as a deep, rumbling tone. The physical difference between a squeak and a rumble is nothing more than frequency. How quickly the wave cycles between its crest and its trough and back again. And there is a close relative of frequency that is worth mentioning, because it makes certain calculations much easier. The period of a wave is simply the time it takes for one complete cycle to occur.
If the frequency is 50 Hz, meaning 50 cycles happen every second, then each cycle takes 1/50th of a second to complete. The period and the frequency are reciprocals of each other. If you know one, you automatically know the other. You simply take one and divide by the value you have. Period is measured in seconds, and it tells you how long you would have to wait, standing in one spot, for one full wave to pass you by. For a deep ocean swell with a period of 10 seconds, you would bob up, sink down, and return to your original height once every 10 seconds. For a sound wave in the middle of the piano keyboard, the period is roughly 1/262nd of a second. The air oscillates back and forth so quickly that each cycle takes about 4 milliseconds. Now here is where these three concepts, wavelength, frequency, and speed, come together in one of the most fundamental relationships in all of physics. And it is beautifully simple. The speed of a wave is equal to its wavelength multiplied by its frequency. Speed equals lambda times f. That is it. Three quantities tied together by multiplication. And this little relationship, this tiny equation that you could write on the back of a receipt, is so powerful that it describes the behavior of every wave you will ever encounter. Sound waves, water waves, light waves, radio waves, seismic waves, gravitational waves. All of them obey this relationship, without exception, always. Let's think about why it has to be true. Because it is not some abstract law handed down from on high. It is just common sense dressed up in mathematical clothing. Suppose a wave has a wavelength of 2 meters. That means each complete cycle of the wave occupies 2 meters of space. Now suppose the frequency is 5 Hz, meaning 5 of those cycles pass a given point every second. If each cycle is 2 meters long, and 5 of them go by in a second, then in 1 second, the wave has covered 10 meters. The speed is 10 meters per second. You are just multiplying the length of one cycle by the number of cycles per second, and out comes the distance covered per second. Speed equals wavelength times frequency. This relationship is useful in so many ways that it is hard to overstate its importance. If you know the speed of sound in air, which is roughly 343 meters per second at room temperature, and you know the frequency of a musical note, you can calculate the wavelength of the sound wave. A concert A, the note to which orchestras tune, has a frequency of 440 Hz. Its wavelength is 343 divided by 440, which is about 78 centimeters. That is roughly the length of your arm from shoulder to fingertip. Every time a musician plays that note, the air in the room is organized into repeating patterns of compression and expansion that are about arm-length long, traveling toward your ears at 343 meters per second, cycling 440 times in every one of those seconds. And your ear somehow sorts all of this out and hands you the experience of a single, clean musical tone. If you know the speed of light, which is roughly 300 million meters per second, and you know the wavelength of a particular color, you can calculate its frequency. Red light has a wavelength of about 700 nanometers. 700 nanometers is 700 billionths of a meter, an almost inconceivably small distance. And yet, when you divide the speed of light by that tiny wavelength, you get a frequency of about 430 trillion Hertz. 430 trillion oscillations per second.
That is how fast the electromagnetic field is vibrating when red light enters your eye. Every color you see, every shade and hue, corresponds to a specific frequency of vibration, so rapid that it makes the fastest sound waves seem glacial by comparison. The equation V equals lambda f is a bridge between the spatial and the temporal. It connects the shape of the wave to the rhythm of the wave, and it does so through the speed at which the wave travels. Change any one of the three, and the others must adjust. In a medium where the speed is fixed, like sound in air at a given temperature, a higher frequency automatically means a shorter wavelength. The cycles come faster, so each one must be shorter to fit the same speed. A lower frequency means a longer wavelength. The cycles come more slowly, so each one stretches out. This is why bass notes have long wavelengths and treble notes have short ones.
This is why radio waves, which have very low frequencies compared to visible light, have wavelengths measured in meters or even kilometers, while gamma rays, with extraordinarily high frequencies, have wavelengths smaller than an atomic nucleus. And with these four ideas, amplitude, wavelength, frequency, and period, you now have the language to describe any wave with precision. You can say how tall it is, how long each cycle is, how quickly it repeats, and how much time each cycle takes. You can calculate the speed if you know the frequency and the wavelength, or the wavelength if you know the speed and the frequency. These are not abstract tools. They are descriptions of things happening in the real world, right now, around you and inside you. But there is something we have been gently ignoring. We have been talking about the shape of waves, their anatomy, their measurements.
We have not yet asked, what kind of motion is the wave actually producing in the material it travels through? When a wave moves through water, the water goes up and down. When a wave moves through air as sound, what does the air do? When light travels through empty space, what exactly is oscillating? The answers to these questions will take us deeper into the paradox, because it turns out that waves do not all move their media in the same way. Some waves shake things sideways. Some waves push and pull things along the direction of travel. And one kind of wave, the most important kind, does not move any medium at all. It moves through nothing, through emptiness, through the void between stars. And what it moves, what oscillates, what rises and falls in that empty space, is not matter. It is something else entirely. That is where we go next. There are, broadly speaking, two ways that a wave can move through a material. Two different dances that the particles of the medium can perform as the wave passes through them. And the difference between these two dances is not a technicality. It is a window into the deep structure of the wave itself, into the relationship between the direction the wave is traveling and the direction the medium is moving. Once you see this distinction clearly, you begin to understand why sound behaves so differently from light, why earthquakes carry two separate kinds of destruction, and why certain waves can travel through things that others cannot. The first dance is the one you already know from watching water. When a ripple moves across a pond, the water bobs up and down. The wave travels horizontally, let's say from left to right, but the water moves vertically, up and down. The direction of the wave's travel and the direction of the water's motion are perpendicular to each other. They are at right angles.
The wave goes one way, and the medium moves in a direction that is 90 degrees different. This kind of wave is called a transverse wave, from the Latin word for across, because the medium moves across the direction of the wave's travel. A transverse wave is like a snake slithering forward, while its body moves from side to side. You can make a transverse wave very easily. Take a long rope, or a garden hose, or a slinky, and stretch it out on the floor. Hold one end and flick your wrist up and down quickly. A hump will travel down the length of the rope, sliding from your hand toward the far end.
That hump is the wave. It moves horizontally. But each little segment of rope is moving vertically, going up as the hump arrives and coming back down as it passes. The rope is dancing the transverse dance, up and down while the pattern goes forward. Now imagine a completely different scenario.
Imagine you are holding that same slinky, but this time, instead of flicking your wrist up and down, you push your hand sharply forward toward the far end and then pull it back. You have compressed the coils near your hand, bunching them together. That compression travels along the slinky as a pulse, a region where the coils are tightly packed, followed by a region where they are stretched apart. The coils themselves are moving in the same direction the wave is traveling, forward and back, push and pull, compress and expand. The direction of the wave's motion and the direction of the medium's motion are now parallel, not perpendicular. This is the second dance. It is called a longitudinal wave, from the Latin word for lengthwise, because the medium moves along the same line as the waves travel. A longitudinal wave is like a crowd doing the wave in a stadium, where each person stands up and sits down, and the pattern of standing and sitting travels around the stadium. But the direction people move, up and down from their seats, well, actually, that is transverse. Let me give you a better picture. A longitudinal wave is more like a traffic jam. Imagine a long, straight highway full of cars. Somewhere ahead, a car brakes suddenly. The car behind it brakes. The car behind that brakes. A region of closely packed, slow-moving cars, a compression, travels backward through the traffic, even though every car is trying to move forward. Then, as cars ahead of the compression speed up and spread out, a region of thinly spaced, fast-moving cars follows. Compression, then expansion. Compression, then expansion. The pattern of bunching and spreading travels along the highway, while each individual car only moves forward and backward along the same line.
And this is exactly how sound works. Sound is a longitudinal wave. When someone speaks, their vocal cords vibrate rapidly, pushing and pulling on the air directly in front of their mouth. That push compresses the air molecules together, creating a tiny region of high pressure. Immediately afterward, as the vocal cords pull back, the air molecules spread apart, creating a tiny region of low pressure. The high-pressure region, the compression, pushes on the air molecules ahead of it, which compress those ahead of them, which compress those ahead of them. The low-pressure region, the rarefaction, follows behind. And so a pattern of alternating high and low pressure travels outward from the speaker's mouth, through the air, across the room, and into your ear. Each individual air molecule barely moves at all. It shifts a tiny distance forward as the compression arrives, then shifts back as the rarefaction follows. It oscillates back and forth around its resting position, just like the water molecule on the surface of a pond oscillates up and down. The air molecule's motion is tiny, perhaps 1/1000th of a millimeter, perhaps even less. But the pattern, the alternation of compression and rarefaction, travels at 343 meters per second. The pattern crosses the room in a fraction of a second. The molecules stay essentially where they are. The paradox again. The sound reaches your ear, but the air does not travel from the speaker to the listener. What moves is the pattern, the pressure variations, the organized sequence of push and pull. And your eardrum, that delicate membrane stretched across your ear canal, responds to those pressure variations by vibrating in sympathy with them, converting the pattern of air pressure into the pattern of electrical signals that your brain interprets as a voice, a melody, a thunderclap, a whisper. Your perception of pitch and loudness,
the two most immediate qualities of any sound you hear, are wired directly into the wave properties we discussed in the previous chapter. Pitch is frequency. Loudness is amplitude. When a violin plays a note, the string vibrates at a specific frequency, and that frequency determines whether you hear a high note or a low note. The harder the bow presses, the greater the amplitude of the string's vibration. The larger the pressure swings in the air, and the louder the note sounds. Your ear is an extraordinarily sensitive detector of these pressure variations. At the threshold of hearing, the faintest sound you can perceive, the air molecules near your eardrum are being displaced by about 10 picometers, roughly 1/10 the diameter of a hydrogen atom. Your ear can detect displacements smaller than the width of an atom. At the other extreme, the threshold of pain, the displacement is about 100 micrometers, roughly the width of a human hair. Between these two extremes lies the entire range of human hearing, from the barely perceptible rustle of a falling leaf to the shattering roar of a rocket engine. A range of amplitudes spanning a factor of about 10 million. Because the human ear can handle such an enormous range of intensities, physicists use a logarithmic scale called the decibel scale to describe sound levels. On this scale, the threshold of hearing is defined as 0 decibels. A whisper is about 20 decibels. Normal conversation is about 60. A lawnmower is about 90. A rock concert might reach 110. And the threshold of pain is about 120 decibels. Every increase of 10 decibels corresponds to the sound intensity increasing by a factor of 10, but your perception of loudness roughly doubling. A sound at 80 decibels does not feel twice as loud as one at 40 decibels, even though it carries 10,000 times as much energy.
The ear compresses the vast range of physical intensities into a much narrower range of perceived loudness, allowing you to function in environments that vary enormously in acoustic energy. And here is something that the natural world exploits in remarkable ways. The range of sounds in nature extends far beyond what human ears can detect. Below 20 Hz, the lower limit of human hearing, lies the realm of infrasound. Elephants communicate using infrasonic rumbles that travel through the ground and through the air, reaching other elephants several kilometers away. Volcanoes, earthquakes, and thunderstorms generate powerful infrasonic waves that can propagate across entire continents. Above 20,000 Hz, the upper limit of human hearing, lies the realm of ultrasound. Bats navigate the darkness by emitting ultrasonic clicks and listening for the echoes, building a three-dimensional acoustic map of their surroundings in real time.
Dolphins use a similar technique underwater, where sound travels fast and far. Even certain moths have evolved the ability to hear bat echolocation calls and take evasive action when they detect them. An evolutionary arms race played out entirely in the domain of ultrasonic waves. Sound traveling through air is the most familiar example of a longitudinal wave, but it is far from the only one. Sound can travel through water, and it does so much faster, about 1,440 meters per second, roughly 4 times faster than in air. The reason is that water molecules are much closer together than air molecules. They are already nearly touching. When one is pushed, it transmits the push to its neighbor almost instantly, because there is so little gap to cross. The same principle explains why sound travels even faster in solids. In steel, sound moves at about 5,000 meters per second.
The atoms in a solid are locked into a rigid crystal lattice, connected by powerful bonds that act like incredibly stiff springs. When one atom is pushed, the push travels along those bonds with extraordinary speed. This is something that French discusses beautifully in his book on vibrations and waves.
The speed of a wave through a medium depends on two things: the stiffness of the medium, meaning how strongly it resists being deformed, and the density of the medium, meaning how much mass is packed into each unit of volume. A stiffer medium transmits waves faster because the restoring forces are stronger and the push travels more quickly from one particle to the next. A denser medium transmits waves more slowly because heavier particles take longer to accelerate and pass the push along. The speed of sound in any material is determined by the balance between these two properties, stiffness and density, and the balance is different for every substance. This is why sound travels fastest in materials that are very stiff but not very dense, and slowest in materials that are dense but not very stiff. It is also why the speed of sound in air depends on temperature. Warm air is slightly less dense than cold air, and the molecules in warm air move faster on average, so they pass the disturbance along more efficiently. On a hot summer day, sound travels a few meters per second faster than on a cold winter night. The difference is small, but it is real, and it is one of the reasons that sounds can seem to carry differently on warm evenings than on cold ones. Now, so far, everything we have discussed has involved a medium, a material substance through which the wave travels. Water for surface waves, air, water, or steel for sound, rope or string for the waves you can make by hand.
In every case, the wave exists because particles of the medium are oscillating, either transversely or longitudinally, and passing that oscillation to their neighbors. The medium is essential. Without it, there is no wave, or so it seems, because now we come to light, and light changes everything. Light is a wave. This was established beyond reasonable doubt in the early 19th century, through experiments that we will examine in detail later in our journey, experiments involving interference and diffraction that only make sense if light is a wave. And light has all the properties we have been discussing. It has a wavelength. Visible light has wavelengths between about 400 nanometers, which your brain perceives as violet, and 700 nanometers, which your brain perceives as red. It has a frequency, staggeringly high frequencies in the hundreds of trillions of hertz. It has amplitude, which determines how intense the light is, how bright it appears.
It has speed, the famous speed of light, approximately 300 million meters per second, the fastest speed at which any information or energy can travel in the universe. Light is a wave, and it obeys the equation V equals lambda times F, just like every other wave. But light does something that no sound wave and no water wave can do. Light travels through a vacuum, through empty space, through the void between Earth and the Sun, between the Sun and the nearest star, between galaxies separated by millions of light years of absolutely nothing. There is no air in space, no water, no rock, no medium of any kind. And yet light crosses those distances effortlessly, carrying energy from the nuclear furnaces of distant stars to the back of your retina, where it triggers the chemical reactions that give you the experience of seeing. This was one of the most disturbing puzzles in the history of physics. If a wave is a disturbance in a medium, and light is a wave, then what is the medium of light? For centuries, physicists assumed there must be one. They called it the luminiferous ether, an invisible, weightless substance filling all of space, providing the something through which light could propagate. But in 1887, Albert Michelson and Edward Morley tried to detect this ether by measuring differences in the speed of light in different directions. If the Earth was moving through the ether, light traveling along that motion should behave differently from light traveling across it. They built an astonishingly precise instrument, mounted it on a stone slab floating in mercury to isolate vibrations,
and measured. They found nothing. The speed of light was the same in every direction. The ether did not exist.
The resolution came from James Clerk Maxwell, who had shown in the 1860s that light was an electromagnetic wave, a self-sustaining oscillation in which a changing electric field creates a changing magnetic field, which creates a changing electric field, leapfrogging through space in an endless chain. And from Albert Einstein, who showed in 1905 that this oscillation did not need a medium. Light was a disturbance in the electromagnetic field itself, and the electromagnetic field existed everywhere, even in empty space, as a fundamental part of the fabric of the universe. This is the ghost. The third kind of wave, transverse waves, move matter perpendicular to the direction of travel. Longitudinal waves move matter parallel to the direction of travel, and electromagnetic waves move no matter at all. What oscillates in a light wave is not any particle.
It is the electric and magnetic fields themselves, rising and falling in strength, perpendicular to each other and perpendicular to the direction the wave is traveling. Light is a transverse wave, but it is not a transverse wave in a material. It is a transverse wave in the fields that permeate empty space. And here, the paradox we have been carrying reaches a new depth. With water waves, we could say that the pattern moves, but the water stays. With sound waves, we could say that the pattern moves, but the air stays. But with light, there is no material to stay behind. The wave is not in anything. It is a traveling pattern in a field, and the field is not made of particles or atoms or molecules. It is something more fundamental, something that exists as part of the structure of space itself. When light travels from the sun to your eye, nothing is delivered. No substance crosses the gap. No particles of solar material arrive at your retina. The energy is carried by a traveling pattern of oscillating fields, and those fields exist in the very space through which the light moves. What is moving? The pattern is moving. What is the pattern in? The field. What is the field made of? That question at the deepest level does not have a simple answer. The electromagnetic field is one of the fundamental ingredients of the universe. It is not made of anything more basic that we currently know of. It simply is, and it can carry waves. And those waves carry energy across the cosmos.
Every photon of light that has ever reached your eye, every radio wave that has ever carried a song to a speaker, every X-ray that has ever passed through your body, every microwave that has ever heated your food, all of them are electromagnetic waves. All of them are oscillations of the same pair of fields, electric and magnetic. All of them obey the same equation, V equals lambda times F. And all of them travel at the same speed in a vacuum, 300 million meters per second, regardless of their wavelength or frequency. The only thing that differs between radio waves and gamma rays, between red light and blue light, between microwaves and X-rays, is the frequency and wavelength. They are all the same phenomenon, playing different notes on the same instrument. And none of them need a medium. None of them move matter. They are patterns in fields, self-sustaining oscillations that propagate through the emptiness of space at the fastest speed the universe allows.
So let's take stock. We have three kinds of waves. Transverse waves in materials, where matter shakes side to side while the wave moves forward. Longitudinal waves in materials, where matter pushes back and forth while the wave moves forward. And electromagnetic waves in empty space,
where no matter moves at all, where only fields oscillate. In all three cases, energy travels. In all three cases, a pattern propagates. And in all three cases, nothing, no substance, no particle, no material object, makes the full journey from source to destination. The energy arrives, the pattern arrives, but the stuff of the universe stays where it is. Something is moving without anything moving. And now we need to ask the question we raised at the very start. If nothing is delivered, how is the energy arriving? How can the sun warm your face from 93 million miles away without sending any material across the gap? What exactly is the energy doing as it travels?
And how much energy can a wave carry? Because the amounts are staggering. The sun delivers enough energy to the Earth every second to power human civilization for hundreds of thousands of years. And every joule of that energy arrives as a wave, as a pattern in a field, as something that moves through nothing. That is the question for the next chapter. Let's begin with something you can feel. Stand outside on a clear day and turn your face toward the sun. Close your eyes. Within a second or two, you feel warmth on your skin. Soft at first, then building. The warmth is real. It is measurable. A physicist with a thermometer and a stopwatch could tell you exactly how many joules of energy your face is absorbing per second. Your skin is being heated by something that traveled 93 million miles across the vacuum of space, through absolute emptiness, through a void with no air and no water and no substance of any kind, and arrived at your skin with enough energy to warm it.
And what delivered that energy was a wave, a pattern of oscillating electromagnetic fields. Nothing more. This should feel remarkable, even after everything we have discussed. Because we are accustomed to the idea that energy must be delivered by something. If someone throws a ball at you and it strikes your hand, you feel the impact. The energy was carried by the ball, a physical object that traveled from the thrower to you. If someone pours hot water into your bath, the heat was carried by the water. If someone turns on a heater and you feel warmth across the room, the heat was carried by convection currents in the air, by actual moving air molecules that absorbed energy from the heater, drifted across the room, and gave up their energy when they reached your skin. In every case, energy was delivered by a material carrier. Something moved from the source to the destination, and the energy rode along. But sunlight is different. Nothing moves from the sun to your face.
No solar material crosses the gap. The photons that warm your skin are not little particles of sun stuff. They are excitations of the electromagnetic field, tiny packets of oscillating energy that propagate through empty space. The sun creates them by nuclear fusion in its core, where hydrogen nuclei slam together at temperatures of 15 million degrees and release energy in the form of gamma rays. Those gamma rays bounce around inside the sun for hundreds of thousands of years, being absorbed and re-emitted and gradually losing energy, shifting to longer wavelengths, until they finally reach the sun's surface and escape into space as visible light, infrared radiation, and ultraviolet light. And then they travel across 93 million miles of nothing, about 8 minutes at the speed of light, and they arrive at your skin, and you feel warmth. The energy carried by electromagnetic waves is immense. The intensity of sunlight at the Earth's surface, on a clear day when the sun is directly overhead,
is roughly 1,000 watts per square meter. That means every square meter of ground receives about 1,000 joules of energy every second. A square meter is roughly the area of a large tabletop. Imagine 1,000 joules of energy arriving at that tabletop every second, delivered by nothing more than oscillating fields. In 1 hour, that square meter receives 3.6 million joules. In 1 day, assuming 6 good hours of sunlight, something like 20 million joules. And this is just 1 square meter. The entire sunlit half of the Earth receives an almost incomprehensible flood of energy, roughly 174 petawatts, continuously from a source 93 million miles away, with no material connection whatsoever. This energy powers the weather. It drives the water cycle. It feeds every plant that has ever grown and, through those plants, every animal that has ever lived. Nearly all the energy in the biosphere ultimately comes from electromagnetic waves that crossed empty space. Waves that carried energy without carrying matter. Patterns that delivered power without delivering substance. The whole living world runs on the energy of a ghost, a self-sustaining oscillation in the electromagnetic field, humming across the void at 300 million meters per second. But how does a wave carry energy? What is the mechanism? We said earlier that each particle in a medium simply oscillates around its resting position as the wave passes through. The water molecule goes up and down. The air molecule goes forward and back. How does energy get transported if the particles themselves are not going anywhere? The answer lies in the timing, in the fact that the particles are not all oscillating at the same moment. They are oscillating in sequence, and that sequence, that coordinated, staggered timing of the oscillations, is what moves energy forward. Think about the line of people again, standing shoulder to shoulder. The first person leans into the second. The second person, receiving a push from the first, gains a little kinetic energy, the energy of motion, and leans into the third. The third person receives that push and passes it to the fourth. At every stage, energy is being transferred from one person to the next. Each person briefly holds the energy as they lean, and then gives it up to their neighbor as their neighbor begins to lean. The energy flows through the line like water through a pipe, even though no person walks from one end to the other. In a wave, the same thing happens on an atomic scale. When a molecule of water rises in a wave, it does so because the molecule next to it pushed it upward. That push involved a transfer of energy.
The rising molecule now has gravitational potential energy because it is above its resting level, and it has kinetic energy because it is moving. As it rises and then begins to fall, it pushes on the molecule ahead of it, transferring some of its energy forward. And that molecule rises and pushes the next, and so on. The energy moves from molecule to molecule, like a baton in a relay race. No single molecule carries the baton very far. Each one holds it for a brief moment, during the fraction of a second that it is oscillating, and then passes it on. But the baton itself, the energy, travels the entire length of the wave. This is why waves are so extraordinarily efficient at transporting energy over long distances. Each individual particle does very little work. It barely moves. It oscillates for a fraction of a second and then settles back down. But the collective effect of millions or billions or trillions of particles doing this in sequence is that energy can travel across an ocean, or across a room, or across a galaxy, without any individual particle making the trip. And now we can ask a very practical question. How does the energy of a wave spread out as it travels? Because waves do spread. Drop a stone in a pond and the ripple expands outward in a growing circle. The further the ripple travels, the larger the circle becomes, and the more the energy is spread out over that expanding perimeter. Each point on the growing circle receives less energy per second than it would have received when the circle was smaller. The wave gets weaker as it spreads. This is why sounds get quieter as you move away from their source. Why lights get dimmer at a distance. Why the warmth of a bonfire fades as you step back from it. The way this spreading works follows a beautiful mathematical pattern.
Imagine a source of waves, something emitting energy in all directions equally. A speaker, a light bulb, a star. The energy radiates outward in a sphere, an expanding shell of wave energy growing in all directions. At a distance of 1 meter from the source, the energy is spread over the surface of a sphere with a radius of 1 meter. The surface area of that sphere is 4 pi times 1 squared, or about 12.5 square meters. At a distance of 2 meters, the radius has doubled, but the surface area has quadrupled because surface area depends on the square of the radius. The same total energy is now spread over a sphere 4 times as large. At 3 meters, the area is 9 times as large. At 10 meters, 100 times. This is the inverse square law. The intensity of a wave, the energy arriving per second per square meter, decreases in proportion to the square of the distance from the source. Double the distance, and the intensity drops to a quarter.
Triple it, and the intensity drops to a ninth. Move 10 times farther away, and the intensity drops to 1/100th. This law governs how light fades across space, how sound diminishes across a field, how the signal from a radio transmitter weakens as you drive away from it. It is one of the most universal patterns in physics, arising not from any property of the wave itself, but simply from the geometry of three-dimensional space. Energy spreading over a growing sphere must thin out as the square of the radius, because the sphere's surface area grows as the square of the radius. There is no escaping this geometry. And this is why, if you know the power of a source and the distance to it, you can calculate exactly how much energy is arriving at any point. The intensity is the power divided by 4 pi r squared. From this you can work out how much solar energy falls on a rooftop, how loud a concert will sound from the back row, how strong a radio signal will be at a receiver.
The equation is simple. The consequences are profound. The entire field of telecommunications, the design of lighting systems, the engineering of concert halls, the planning of solar energy installations, all of these depend on this one relationship between energy, distance, and the geometry of spreading waves. There is one more thing about wave energy that we should note before moving on, because it connects back to something we said about amplitude. The energy carried by a wave is proportional to the square of its amplitude. A wave that is twice as tall carries 4 times as much energy. A wave 3 times as tall carries 9 times as much. This is true for all kinds of waves: water, sound, light, all of them. And it explains why large waves are so much more destructive than small ones. A tsunami that is 2 meters tall at sea level carries 4 times the energy of one that is 1 meter tall.
An earthquake that produces ground motion with twice the amplitude of another is 4 times as energetic. A shout that is 3 times louder than a whisper in terms of the amplitude of the pressure oscillations carries 9 times more energy. The square relationship between amplitude and energy also means that very small increases in amplitude can produce disproportionately large increases in energy. This is why the difference between a moderate breeze and a strong wind can be the difference between gentle ripples and towering waves. The wind does not need to double the wave height to double the destructive potential. It just needs to increase it by about 40%, because 1.4 squared is roughly 2. a modest increase in amplitude can unlock a dramatic increase in energy. And so we arrive at a picture that is, in its own way, quite moving. Waves carry energy without carrying matter.
They do this through the sequential, cooperative oscillation of countless individual particles, each one doing a tiny amount of work, passing a small amount of energy to its neighbor, and then settling back to rest. The energy spreads as it travels, thinning out over an expanding wavefront in accordance with the inverse square law. And the amount of energy carried is determined by the amplitude and the frequency of the wave, encoded in the height and speed of those oscillations. Every sound you hear is energy that arrived at your ear without any air traveling from the source to your eardrum. Every beam of light you see is energy that arrived at your eye without any matter crossing the intervening space. Every time you feel the warmth of the sun, you are receiving energy that was transported 93 million miles by a pattern of oscillating fields, carried through the vacuum of space by nothing at all. Something travels, something carries energy, but it is not a thing.
It is a pattern, a relationship, a coordination among countless tiny oscillations. And the universe has decided that this is enough, that energy can flow, information can be transmitted, and the whole world can be connected without any material ever making the trip. We have now described the birth of a wave, the language we use to measure it, the ways it moves through different media, and the energy it carries as it goes. But there is one property of waves we have not yet discussed, a property so subtle that you could live your entire life surrounded by waves and never notice it, but so important that it governs whether waves build each other up or tear each other apart. It is the property that determines whether two sound waves combine into a louder note or cancel into silence, whether two beams of light produce bright bands or darkness, whether the waves in a harbor calm each other or amplify into something dangerous. That property is called phase,
and it is the key that unlocks everything that comes next. Every oscillation has a rhythm. A swing goes back and forth. A pendulum ticks left and right. A water molecule on the surface of a pond rises, falls, and rises again. In each case, there is a cycle, a complete round trip from one position through all the others and back to the start. And at any given moment, the oscillating thing is somewhere in that cycle. It might be at the very top, the crest, having just reached its highest point and about to begin its descent. It might be at the very bottom, the trough, about to start climbing again. It might be crossing through the middle on its way up, or crossing through the middle on its way down. Each of these positions is a different point in the cycle, a different moment in the ongoing rhythm of the oscillation. Phase is the word we use to describe where an oscillation is within its cycle at any given moment.
and the easiest way to think about it is to imagine a clock, though a special kind of clock, one that goes around once for every complete cycle of the wave. Picture a clock with a single hand, and imagine that this hand sweeps around the dial once for every complete oscillation. When the hand is at 12 o'clock, the wave is at its resting position and moving upward. When the hand reaches 3 o'clock, the wave has climbed to its crest. At 6 o'clock, it is back at the resting position and moving downward. At 9 o'clock, it is at the trough, and when the hand returns to 12, the wave has completed one full cycle and is starting over. Every position on the clock face corresponds to a specific position in the wave's cycle. Physicists do not usually describe phase in terms of clock positions, of course. They use angles, measured in degrees or radians, because one full cycle of a wave corresponds to a full circle, 360 degrees, or 2 pi radians. The crest is at 90 degrees, or pi over 2 radians. The midpoint heading downward is at 180 degrees, or pi radians. The trough is at 270 degrees, or 3 pi over 2. And when you return to the start, you have gone through 360 degrees. This might sound abstract, but it has a very concrete meaning. If someone tells you that a wave is at a phase of 90 degrees, they are telling you that the wave is at its crest. If they say it is at a phase of 270 degrees, it is at the trough. The phase tells you the wave's position in its ongoing cycle, like a snapshot of where the oscillation is at one specific instant. Now here is why this matters, and why it matters so much that everything else we are going to discuss, interference, standing waves, diffraction, all of it depends on understanding phase. When a single wave travels through a medium, phase is interesting but not particularly dramatic.
The wave has a phase at every point along its length, and that phase changes smoothly from point to point. At the crest, the phase is 90 degrees. A quarter wavelength later, it is 180 degrees. Another quarter wavelength, 270. The phase increases continuously as you move along the wave, ticking through the full 360 degrees once for every complete wavelength. But the moment two waves exist in the same space, phase becomes the most important property in the universe, because the relationship between the phases of two overlapping waves determines whether those waves will cooperate or destroy each other. Two waves in the same medium, arriving at the same point with the same frequency, will either amplify each other into something larger or cancel each other into nothing. And the only thing that determines which of those outcomes occurs is their relative phase, the difference between their positions in their respective cycles, the gap between their hidden clocks. Let's build this picture slowly, because it is worth getting right. Imagine two waves traveling through the same stretch of water, arriving at the same point from two different directions. Both have the same wavelength and the same amplitude. They are identical waves in every measurable way, and suppose they arrive at this point perfectly synchronized, crest arriving at the same moment as crest, trough arriving at the same moment as trough. Their hidden clocks are aligned. Their phases are identical. At every moment, both waves are at the same position in their cycles. When two waves overlap like this, the displacement at the point where they meet is the sum of their individual displacements. This is one of the most important principles in wave physics, and it goes by the somewhat grand name of the principle of superposition. When two waves overlap, the resulting displacement is simply the sum of the displacements that each wave would produce on its own. If both waves are at their crests at the same moment, the combined displacement is twice the crest height. If both are at their troughs, the combined trough is twice as deep. The two waves, perfectly in phase, produce a combined wave that is twice as tall. This is called constructive interference, and it happens whenever two waves are in phase, meaning their cycles are synchronized, their hidden clocks are aligned, and their crests and troughs arrive at the same moments. You can hear constructive interference easily. If two speakers are playing the same note at the same volume, and you stand at a point where the sound waves from both speakers arrive in phase, the note sounds louder, noticeably louder. The two waves are cooperating, each one adding its displacement to the other, producing a combined wave with a larger amplitude and therefore more energy.
The loudness you hear is the direct result of two synchronized patterns of compression and rarefaction arriving at your ear at the same time, reinforcing each other. Now imagine the opposite. The same two waves, same wavelength, same amplitude, arriving at the same point. But this time, they are perfectly out of phase. One wave's crest arrives at exactly the same moment as the other wave's trough. When one is pushing the water up, the other is pulling it down. When one is compressing the air, the other is expanding it. Their hidden clocks are exactly half a cycle apart. The phase difference between them is 180 degrees, or pi radians, exactly half of a full cycle. When you add these two waves together, using the principle of superposition, something astonishing happens. The crest of one wave is exactly as tall as the trough of the other is deep. They are mirror images. At every point, the upward displacement of one wave is exactly cancelled by the downward displacement of the other. The sum is zero. The combined wave has zero amplitude. No displacement, no oscillation, nothing. The water is flat. The air is still. The point where the two waves meet is silent. This is called destructive interference, and it is one of the most counterintuitive phenomena in all of physics. Two waves, each carrying energy, each producing oscillation, arrive at the same point and produce stillness. Two sounds produce silence. Two lights produce darkness. It seems impossible, almost paradoxical. How can two somethings add up to nothing? The answer is that waves are not objects, they are displacements. They are patterns of positive and negative deviation from a resting state, and positive and negative numbers can add up to zero. A crest of +5 centimeters and a trough of -5 centimeters sum to 0 centimeters. An air compression of +1 Pascal and a rarefaction of -1 Pascal sum to 0. The mathematics is simple, but the physical reality is astonishing. Two waves, each perfectly real, each carrying energy, can overlap in such a way that neither one is detectable. They are still there. Both waves continue to propagate beyond the point of cancellation. But at that one point, at that one moment, they conspire to produce nothing. This is not a theoretical curiosity. It is something you encounter in daily life, though you may not recognize it. If you have ever worn noise-cancelling headphones, you have experienced destructive interference directly. The headphones contain a microphone that picks up ambient noise, a small computer that analyzes the waveform, and a speaker that produces a wave with the same amplitude but opposite phase. The anti-noise wave is carefully timed so that its crests line up with the noise's troughs, and vice versa. The result is that the noise and the anti-noise cancel each other, producing dramatic silence, or at least a dramatic reduction in noise. You are hearing destructive interference in action, two waves summing to 0, engineered on purpose to make your commute quieter. Noise-cancelling headphones work well for low-frequency sounds, the steady drone of an airplane engine or the rumble of a train, because those sounds have long wavelengths and change slowly, giving the computer time to analyze and respond. They work less well for sudden, sharp sounds, like someone clapping or a dog barking, because those sounds contain rapidly changing frequencies, and the computer cannot generate the anti-wave quickly enough.
But for steady, low-frequency noise, the cancellation can be remarkable. Two waves entering your ear, one from the outside world and one from the speaker, summing to nearly zero, producing a pool of quiet in the middle of a noisy environment.
But phase differences are rarely all or nothing.
Waves in the real world are not always perfectly in phase or perfectly out of phase. Most of the time, the phase difference is somewhere in between. And when it is, the result is a partial combination. Neither full constructive interference nor full destructive interference, but something in between. The combined wave has an amplitude that is somewhere between 0 and twice the original. Think of it this way. Two waves are like two people pushing a swing. If they push at exactly the same moment in the swing's cycle, the swing goes higher and higher. That is constructive interference. If one pushes while the other pulls, at exactly the wrong moment, the swing slows down and eventually stops. That is destructive interference.
But if they push at slightly different moments, neither perfectly timed nor perfectly mistimed, the swing goes a bit higher than one person could manage, but not as high as two perfectly coordinated pushers would achieve. The result depends entirely on the timing, on the phase relationship between the two pushes. And this is why phase matters so much. Because in the real world, waves from multiple sources are constantly overlapping, constantly combining, and the pattern of their combination, the pattern of places where they reinforce and places where they cancel, create some of the most beautiful and most important phenomena in all of physics. Interference patterns are everywhere. In the ripples on a pond when two stones are dropped simultaneously. In the shimmering colors on a soap bubble or an oil slick. In the bright and dark bands that appear when two beams of coherent light overlap. In the acoustics of concert halls, where the placement of walls and ceilings creates regions of reinforcement and cancellation that profoundly affect what the audience hears. Phase is the hidden clock inside every wave. You cannot see it directly, any more than you can see the internal timing of a pendulum just by looking at a photograph. But it is always there, ticking away inside the oscillation, determining how that wave will interact with every other wave it encounters. And those interactions, the constructive and destructive interferences, the patterns of reinforcement and cancellation, are not incidental effects. They are some of the most fundamental behaviors that waves exhibit. They are the reason that waves do things that no solid object can do. And they are the gateway to the most surprising discovery in the history of wave physics. The discovery that light is, beyond any doubt, a wave.
That discovery was made by a man named Thomas Young, in an experiment so simple and so elegant that it remains one of the most beautiful demonstrations in all of science. And the phenomenon it revealed, the phenomenon of interference patterns produced by two sources of waves, leads directly to an even deeper behavior, one that waves exhibit when they encounter obstacles, when they meet edges and apertures and barriers, when they do something that no particle could ever do. They bend, they reach around corners, they spread into shadows. That behavior has a name, and the name is diffraction. And understanding it will change the way you see the world. So now we know what phase is, the hidden clock ticking inside every oscillation, tracking where the wave is in its cycle at any given moment. And we know that the relationship between the phases of two overlapping waves determines whether they reinforce or cancel. Let's see what that looks like in the real world. Because in 1801, a young English physician named Thomas Young stood in a darkened room and did something that, on the face of it, should have been unremarkable. He let a beam of sunlight enter the room through a tiny hole in the window blind. That beam of light, narrow and bright, fell upon a screen on which he had cut two very thin, closely spaced slits. Two parallel openings barely a fraction of a millimeter apart. Behind this screen, on a far wall, he placed a white surface and observed what happened when the light passed through the two slits. What he expected, or what many of his contemporaries would have expected, was simple. Two bright lines on the wall, one from each slit, side by side. Light travelling in straight lines from the source through each slit and illuminating two narrow strips on the wall. This is what you would expect if light were made of tiny particles, which was the dominant theory at the time, championed by no less a figure than Isaac Newton himself.
Particles travel in straight lines. They pass through openings. Two openings should produce two lines. What Young actually saw was something completely different. On the white wall behind the two slits, there was not a pair of bright lines. There was a pattern, an alternating sequence of bright bands and dark bands equally spaced, stretching across the wall like the teeth of a comb. Bright, dark, bright, dark, bright, dark. A pattern that had no business existing if light were simply a stream of particles. Because particles passing through two slits should produce two clusters of hits, not an alternating pattern of presence and absence. But the pattern made perfect sense if light were a wave. To understand why, let's step back from light for a moment and think about water, because interference patterns in water are something you can see with your own eyes. In a bathtub, or a pond, or even a sink full of water.
Imagine a calm surface of water, and imagine that you touch the surface simultaneously at 2 points, perhaps by dipping 2 fingertips into the water at the same time, a few centimeters apart. Each finger creates a set of circular ripples radiating outward, and very quickly those 2 sets of ripples begin to overlap. What you see is not just a chaotic mess of crossing waves. You see a pattern. In some places, the ripples from the 2 sources arrive in phase. Crest meets crest, trough meets trough. The water in those places oscillates with a large amplitude, rising higher and falling deeper than either set of ripples alone would produce. In other places, the ripples arrive out of phase. Crest meets trough. The water in those places is nearly flat, barely moving, because the 2 waves are cancelling each other.
The result is a striking pattern of alternating agitation and calm. Lines of vigorous oscillation separated by lines of near stillness, radiating outward from the 2 sources like the spokes of a fan. These lines of calm are the most interesting. They are points of destructive interference, places where the 2 waves are always arriving half a cycle apart, always cancelling. And the reason they form lines, rather than random dots, is because of the geometry. There are specific paths through the water where the distance from one source and the distance from the other source differ by exactly half a wavelength. At those points, one wave has travelled half a wavelength farther than the other, which means it arrives exactly half a cycle behind. Crest meets trough. Cancellation, silence, stillness. And the set of all such points, where the path difference is half a wavelength, forms a smooth line curving across the water's surface. Similarly, there are lines where the 2 distances differ by exactly 1 full wavelength, or 2 full wavelengths, or 3. At those points, one wave has travelled a whole number of wavelengths farther than the other, which means it arrives in phase. Crest meets crest. Reinforcement. Large oscillation. And those points form their own lines, the lines of constructive interference, the bright bands of vigorous motion. This is exactly what Thomas Young saw with light, translated from the surface of water
to a beam of sunlight passing through two slits. Each slit acted as a source of light waves, just as each fingertip acted as a source of water waves. The light spreading from the two slits overlapped on the far wall, and because light is a wave, because it has phase, because it follows the principle of superposition, the overlapping light produced an interference pattern. Bright bands where the light from the two slits arrived in phase and reinforced each other.
Dark bands where the light arrived out of phase and cancelled. The dark bands are the remarkable thing. They are regions of genuine darkness on the wall. Two sources of light shining on the same spot, producing darkness. Not dimness. Darkness. Absence of light. Two beams arriving at the same point and adding up to zero. This cannot happen if light is made of particles. Particles cannot cancel. If you throw two handfuls of sand at the same spot on a wall, you get more sand, never less. But waves can cancel, because waves are displacements, and positive and negative displacements can sum to zero. Young's experiment was decisive evidence that light is a wave. The interference pattern he observed could not be explained by any particle theory. Only a wave theory, with its concepts of wavelength, phase, and superposition, could account for those alternating bands of brightness and darkness. And Young went further.
By measuring the spacing of the bands and the distance between the slits, he was able to calculate the wavelength of the light he was using. He found it to be astonishingly small, on the order of a few hundred nanometers, a few 10,000ths of a millimeter. This was the first measurement of the wavelength of light, and it was achieved through the principle of interference, through the visible consequences of waves combining and cancelling. Young's double-slit experiment, as it has come to be known, is one of the most important experiments in the history of physics. It established the wave nature of light beyond reasonable dispute, and it demonstrated that waves, because they have phase, because they can interfere, produce patterns that no collection of particles ever could.
The experiment is so fundamental that it has been repeated with every kind of wave imaginable, with water, with sound, with microwaves, with electrons, even with individual photons sent through the slits one at a time. And in every case, the interference pattern appears. The alternating bright and dark bands, the signature of waves combining and cancelling, emerge with mathematical precision, governed by the wavelength of the wave and the geometry of the slits. Now, let's consider a particularly beautiful consequence of interference, one that you have almost certainly encountered without realizing what you were seeing. Have you ever noticed the shimmering colors on a soap bubble, the rainbow patterns that shift and flow across the bubble's surface as it floats and rotates? Those colors are produced by interference. A soap bubble is a thin film of soapy water, incredibly thin, just a few hundred nanometers thick. When white light, which contains all the wavelengths of visible light mixed together, strikes the surface of the bubble, some of it reflects off the outer surface, and some passes through and reflects off the inner surface. These two reflected beams, one from the outside and one from the inside of the film, travel slightly different distances before reaching your eye. The beam that reflected off the inner surface had to travel through the thickness of the film twice, once going in and once coming back out. That extra distance is very small, but it is enough to create a phase difference between the two reflected beams. For some wavelengths, that phase difference puts the two beams in phase. Constructive interference. That wavelength is reinforced and you see a bright color. For other wavelengths, the phase difference puts the beams out of phase. Destructive interference. That wavelength is cancelled and you do not see it. The color you see at any particular point on the bubble
is the wavelength that happens to interfere constructively at that thickness of the film. As the film's thickness varies across the surface of the bubble, because gravity is pulling the soapy water downward and the film is thicker at the bottom than at the top, different wavelengths are reinforced at different points. The result is the shimmering, shifting rainbow pattern that makes soap bubbles so mesmerizing. The same physics explains the rainbow sheen of oil slicks on wet pavement, the iridescent colors on the wings of certain butterflies and beetles, and the spectrum of colors you see when you tilt a CD or DVD in the light. In each case, thin film interference or surface structure interference is selectively reinforcing some wavelengths and cancelling others, producing vivid colors from the interaction of waves.
There is another form of interference that deserves special attention because it produces something extraordinary, a wave that appears to stand still. This is called a standing wave, and it occurs when two identical waves traveling in opposite directions overlap in the same medium. Imagine a guitar string. When you pluck the string, a wave travels along it from your finger toward one end. When it reaches the end, which is fixed, the wave reflects and travels back in the opposite direction. Now you have two waves on the string, one going left and one going right, with the same frequency and wavelength and amplitude. As these two waves pass through each other, they interfere. At certain points along the string, the interference is always destructive. The two waves always cancel, and the string at those points does not move at all. These are nodes, points of permanent stillness. At other points, the interference is always constructive.
The two waves always reinforce, and the string at those points oscillates with maximum amplitude. These are antinodes, points of maximum vibration. The result is a wave that does not appear to travel. The pattern of oscillations stays in place. The nodes stay still. The antinodes bounce up and down. The string vibrates in a fixed pattern, like a skipping rope held at both ends and shaken just right. This standing wave is what produces the musical tone you hear when a guitar string vibrates. The frequency of the tone depends on the length of the string, the tension in the string, and the mass of the string, all of which determine the speed of waves on the string, and therefore the wavelength and frequency of the standing wave pattern that fits neatly between the two fixed ends. Different standing wave patterns can exist on the same string, depending on how many nodes and antinodes fit between the endpoints.
The simplest pattern, called the fundamental or first harmonic, has just two nodes, one at each end and one antinode in the middle. The string bulges out in a single arc, like a jump rope. The next pattern, the second harmonic, has three nodes and two antinodes, and the string vibrates in two halves, each arcing in opposite directions. The third harmonic has four nodes and three antinodes, and so on. Each harmonic has a frequency that is a whole number multiple of the fundamental frequency. The second harmonic is twice the fundamental. The third is 3 times. The fourth is 4 times. This is why musical strings can produce not just a single tone, but a rich blend of tones, the fundamental and its harmonics, called overtones, all sounding simultaneously, each with a different amplitude, combining to give the instrument its characteristic timbre, its sonic signature, the quality that makes a violin sound different from a guitar, even when both play the same note.
Standing waves are not limited to strings. They occur in air columns inside flutes, clarinets, and organ pipes. When you blow across the top of a bottle, the air inside vibrates in a standing wave pattern, with a node at the closed bottom and an antinode at the open top. The length of the air column determines the wavelength and therefore the pitch. Shorter columns produce higher notes. This is why a nearly empty bottle produces a lower tone than one that is nearly full, because the column of air above the water is longer in the empty bottle, supporting a longer wavelength and a lower frequency. the same principle governs the design of pipe organs, where each pipe is cut to a precise length to produce a specific note, the longest pipes for the deepest bass notes and the shortest for the highest treble. Standing waves occur on the surfaces of drums, though in 2 dimensions rather than 1, producing complex patterns of vibrating regions and nodal lines. If you scatter fine sand on the surface of a drum and tap it, the sand collects along the nodal lines, the lines where the surface is not vibrating, revealing the standing wave pattern in visible form. These patterns, first studied systematically by the German physicist Ernst Chladni in the late 18th century, are called Chladni figures, and they can be strikingly beautiful, geometric arrangements of lines and curves that map out the modes of vibration of the surface. Standing waves also occur in the oscillation of bridges and buildings during earthquakes, sometimes with disastrous consequences when the frequency of seismic waves matches the natural frequency of the structure and drives it into resonance, building up enormous oscillations through repeated constructive interference. Every physical object, every bridge, every building, every wine glass, every stretch of air inside a tube has a set of natural frequencies at which it prefers to vibrate.
These are the frequencies of its standing wave modes, the patterns of oscillation that fit neatly within its boundaries. When an external force pushes the object at one of these natural frequencies, the object responds with disproportionate enthusiasm. Each push adds energy to the standing wave, because each push arrives in phase with the existing oscillation, reinforcing it constructively. The amplitude grows with each cycle, sometimes building to dramatic or dangerous levels. This is resonance, and resonance is, at its core, interference sustained over time. When you push a swing at exactly the right moment in its cycle, each push arrives in phase with the swing's natural oscillation, adding energy constructively. The amplitude builds with each push, growing larger and larger. If you push at the wrong moment, out of phase, your push fights the swing's natural motion, and the amplitude decreases. The difference between building up the swing and slowing it down is nothing more than timing. Phase. Resonance explains why a singer's voice can shatter a wine glass. The glass has a natural frequency, determined by its shape, its thickness, and the material it is made of. If the singer produces a note at exactly that frequency and sustains it with enough intensity, each cycle of the sound wave adds a tiny amount of energy to the glass's vibration, arriving in phase, reinforcing the oscillation. The amplitude of the glass's vibration grows and grows until the glass cannot sustain it any longer. The material reaches its breaking point, and the glass shatters, destroyed by the accumulated energy of hundreds of tiny constructive pushes. Resonance is why soldiers were traditionally told to break step when crossing a bridge. If a column of soldiers marches in perfect rhythm, and if the frequency of their footfalls happens to match a natural frequency of the bridge, each footfall adds energy to the bridge's oscillation. Over many steps, the amplitude can build to the point where the bridge sways dangerously. By breaking step, by walking out of rhythm with each other, the soldiers ensure that their footfalls arrive at random phases, some reinforcing and some cancelling the bridge's natural oscillation, preventing the build-up. The most dramatic historical example occurred in 1831, when a column of British soldiers marching across Broughton Suspension Bridge near Manchester caused the bridge to sway so violently that it collapsed. Since then, the order to break step on bridges
has become standard practice in military training. Resonance explains why your car sometimes vibrates at a particular speed, but not at slightly higher or lower speeds.
At that speed, the engine's vibration frequency matches a natural frequency of the car's body or suspension. The vibrations build up, making the car shudder. Speed up or slow down, and the frequency shifts away from the resonance and the vibration fades. And resonance, in its gentlest form, is what you experience when you run a wet finger around the rim of a wine glass. Your finger does not force the glass to vibrate at some arbitrary frequency. It provides a sustained, gentle excitation, and the glass responds at its own natural frequency, the one that comes most easily to its structure. The tone you hear is pure and clear because it is the glass singing its own song, the standing wave that fits most naturally within its walls, sustained by the continuous energy input of your circling finger. Interference in all its forms, constructive and destructive, thin film and double slit, standing waves and resonance, arises from the fundamental nature of waves as oscillations with phase.
Because waves have phase, they can be synchronized or desynchronized. Because they obey the principle of superposition, their displacements add. And because positive and negative displacements can sum to any value, including zero, the meeting of waves can produce results that range from dramatic amplification to complete cancellation. We have now seen what waves do when they meet each other in open space. But there is one more behavior, one more trick that waves perform, that solid objects cannot. And it is perhaps the most surprising of all. What happens when a wave encounters an obstacle? A wall, a doorway, the edge of a cliff, an opening in a barrier. If waves were like particles, traveling in straight lines, they would simply be blocked by the obstacle, casting a sharp shadow on the far side. The region behind the obstacle would be silent, dark, undisturbed, as clean and complete as the shadow cast by a building on a sunny day. But waves do not do this.
Waves do something strange, something that violates every intuition you have about things that travel in straight lines. When a wave encounters an edge or passes through an opening, it bends, it curves, it spreads into the region behind the obstacle, filling in the shadow, reaching around the corner, arriving where straight-line travel could not possibly deliver it. You experience this every day. When someone calls your name from another room, you hear them even though you cannot see them. The sound wave bends around the doorframe, curves into the hallway, spreads into the room where you are sitting. You hear the voice clearly, despite the fact that there is no straight path between the speaker and your ear. If sound traveled in perfectly straight lines, you would hear nothing from around a corner.
The fact that you do, the fact that sound fills rooms and bends around obstacles and reaches into spaces that are geometrically hidden from the source, is evidence of one of the most fundamental properties of waves. That property is called diffraction, and it is the subject of the next chapter. Imagine you are standing in a hallway and someone at the far end shouts your name. You hear them clearly. The sound travels down the hallway in a more or less straight line, and your ears pick it up without difficulty. Now imagine that the person steps around the corner into another corridor. You can no longer see them. There is a solid wall between you, and yet, when they shout your name again, you still hear them. The sound is quieter perhaps, and it may sound a bit different, but it is unmistakable. The voice has reached you despite the fact that there is no straight path from their mouth to your ear.
If sound were made of tiny particles flying through the air in straight lines, this would be impossible. A particle traveling in a straight line from the speaker's mouth would hit the wall and stop. The region around the corner would be silent, shielded by the wall. But sound is a wave, and waves do something that no particle can do. They bend around obstacles, they spread through openings, they fill in shadows. This bending, this spreading, this refusal to stay confined to straight-line paths is called diffraction. And it is one of the defining characteristics of wave behavior, one of the properties that most clearly distinguishes waves from particles, and one of the keys to understanding why the world looks, sounds, and feels the way it does. Diffraction happens whenever a wave encounters an edge, a boundary, an obstacle, or an opening. When a wave passes through a doorway, it does not continue as a narrow beam the width of the door.
It fans out on the other side, spreading to the left and to the right, filling the room beyond the door with sound or light. When a wave encounters a barrier with a small opening in it, the wave that passes through the opening spreads outward in all directions on the far side, as if the opening itself were a new source of waves, radiating energy in a semicircle. To understand why this happens, we need to return to something fundamental about how waves propagate. We said earlier that a wave moves through a medium because each part of the medium, each molecule, or each patch of field oscillates and pushes its neighbour into oscillating. The wave is a chain of nudges, each one passing the disturbance forward. Now, when a wave arrives at an opening in a barrier, the parts of the wave that are blocked by the barrier stop. They cannot pass through solid material, so they are absorbed or reflected. But the parts of the wave that are within the opening continue through.
And the key insight is this: each point within the opening acts as a tiny source of waves in its own right, radiating energy outward in all directions. This idea was first articulated by the Dutch physicist Christiaan Huygens in the 17th century, and it is known as Huygens' principle. Every point on a wavefront can be thought of as a source of tiny secondary wavelets that spread outward, and the new wavefront at any later time is the sum, the superposition, of all those secondary wavelets. When the wave is traveling through open space, with no barriers, all of these secondary wavelets add up in such a way that the wave continues in a straight line. The wavelets from the edges of the wavefront happen to cancel in most directions and reinforce only in the forward direction. But when part of the wavefront is blocked by a barrier, the cancellation is incomplete.
The wavelets from the exposed part of the wavefront, the part within the opening, spread outward without being opposed by wavelets from the blocked regions. The result is that the wave fans out, spreading beyond the geometric shadow of the barrier, reaching into regions that straight-line travel would never access. The amount of spreading depends on the relationship between the wavelength of the wave and the size of the opening. This relationship is absolutely crucial, and it explains so many everyday observations that it is worth stating clearly. Diffraction is most pronounced when the wavelength is comparable to the size of the opening or obstacle. If the opening is much larger than the wavelength, diffraction is minimal. The wave passes through the opening mostly as a straight beam, with only slight spreading at the edges.
If you shine a flashlight through an open door, the beam of light does not fan out dramatically on the other side because the wavelength of light, a few hundred nanometers, is inconceivably smaller than the width of the door, roughly a meter. The ratio is about 1 to 2 million. At that ratio, diffraction is negligible. The light behaves almost exactly as if it were traveling in straight lines. But if the opening is comparable in size to the wavelength, diffraction is dramatic. The wave spreads out widely, almost as if the opening were a point source radiating in all directions. Sound waves have wavelengths ranging from about 1 centimeter for very high-pitched sounds to several meters for low-pitched sounds. A doorway is about a meter wide. For low-frequency sounds, the wavelength is similar to the doorway width, and diffraction is strong. The sound fans out vigorously on the other side of the door, filling the next room.
For high-frequency sounds, the wavelength is much shorter than the doorway, and diffraction is weaker. The sound passes through more as a directed beam, with less spreading. This is why you can hear bass notes from around corners more easily than treble notes. The bass notes have long wavelengths that diffract strongly around obstacles and through openings. The treble notes have short wavelengths that diffract less and tend to travel in more direct lines. If you have ever stood outside a nightclub or a concert venue, you may have noticed that the sound you hear most clearly is the bass, the thump of the kick drum, the rumble of the bass guitar. The treble, the cymbals, the vocals, the high harmonics are much harder to hear from outside. The walls of the building block the treble quite effectively because those short wavelengths do not diffract well around the edges of the windows and doors.
But the bass diffracts easily,
bending around corners and through gaps, reaching you with surprising persistence. The same principle explains why AM radio can reach you inside a building, but FM radio often cannot. AM radio uses wavelengths on the order of hundreds of meters, enormously long compared to any building. These waves diffract around buildings, hills, and other obstacles with ease. FM radio uses wavelengths on the order of a few meters, much shorter. And though they still diffract somewhat, they are more easily blocked by large structures. This is also why AM radio stations can be heard at great distances, especially at night when the ionosphere reflects them, while FM stations typically have a range limited to the line of sight from the transmitter. Whales exploit this same physics across entire ocean basins. The low-frequency songs of blue whales and fin whales, some as deep as 10 or 15 hertz, produce sound waves with wavelengths of 100 meters or more.
At those wavelengths, most underwater obstacles, seamounts, ridges, even entire islands, are smaller than the wave. The sound diffracts around them effortlessly, bending and spreading as though the obstacles were barely there. Combined with the fact that sound travels efficiently through water, these whale songs can propagate across thousands of kilometers, reaching other whales on the far side of an ocean. Before commercial shipping filled the seas with noise, a blue whale in the mid-Atlantic could, in principle, be heard by another blue whale near the coast of Africa. The animal had discovered, through millions of years of evolution, what physicists would later formalize. If you want your signal to travel far and bend around every obstacle in its path, use a long wavelength. Earthquakes offer another vivid example. When a fault ruptures, it sends seismic waves radiating outward through the Earth's crust and mantle. These waves come in several varieties. The primary waves, called P waves, are longitudinal, compressing and expanding the rock along the direction of travel, much like sound waves in air. The secondary waves, called S waves, are transverse, shaking the rock perpendicular to the direction of travel. Both types diffract as they encounter the boundaries between layers of the Earth, the transitions between crust and mantle, between mantle and outer core, between outer core and inner core. The way they diffract, the angles at which they bend, the shadows they cast on the far side of the Earth, were the clues that allowed seismologists in the early 20th century to map the Earth's internal structure without ever digging deeper than a few kilometers.
The entire picture of the Earth's layered interior, the liquid outer core, the solid inner core, the density profiles of the mantle, was deduced from the diffraction patterns of seismic waves, read like a diagnostic image by scientists who understood how waves bend around obstacles whose size is comparable to their wavelength. Even the atmosphere itself diffracts sound in ways that shape your daily experience. On a calm evening, you may notice that sounds carry further than during the day.
voices from a distant park, the hum of a highway, the bark of a dog far away, all seem to reach you more clearly after sunset. Part of the reason is that the atmosphere is quieter at night, with less background noise to mask distant sounds. But part of the reason is diffraction caused by temperature gradients.
During the day, the air near the ground is warmer than the air above, and sound waves traveling near the surface are bent upward, away from listeners, because sound travels faster in warm air, and the wave's lower edge outpaces its upper edge, curving the wavefront upward. At night, the temperature gradient often reverses. The ground cools quickly, and the air near the surface becomes cooler than the air above. Sound waves are now bent downward toward the ground, curving toward listeners and allowing distant sounds to reach much farther than during the day. This bending of waves due to variations in speed is technically called refraction rather than diffraction, but it arises from the same underlying mechanism, Huygens' principle at work, with different parts of the wavefront traveling at different speeds and the resulting curvature directing the wave in surprising directions. Now, here is where diffraction connects back to interference in a profound and beautiful way. When a wave passes through a single slit in a barrier, it does not simply fan out uniformly. It creates a pattern. On a screen placed behind the slit, you would see a bright central band, the main concentration of wave energy, flanked by alternating dark and bright bands that become progressively fainter as you move away from the center. This pattern is called a single-slit diffraction pattern, and it is caused by interference among the secondary wavelets coming from different parts of the slit. Here is how to think about it. Imagine the slit divided into many tiny segments, each one acting as a source of secondary wavelets, as Huygens described. In the forward direction, straight ahead from the slit, all of these wavelets are in phase. They all travel the same distance to the center of the screen. They arrive together, crest aligned with crest, and they reinforce, producing a bright band. But at a slight angle to the forward direction, the wavelets from different parts of the slit travel slightly different distances. Some arrive in phase and reinforce, others arrive out of phase and cancel. The net result depends on the exact geometry, but at certain specific angles, the cancellation is complete. Every wavelet from the top half of the slit is exactly out of phase with a corresponding wavelet from the bottom half. The total cancellation produces a dark band. At slightly larger angles, the wavelets partially reinforce again, producing a dimmer, bright band, then another dark band, then another dim, bright band, and so on, in a pattern of decreasing intensity that spreads across the screen. The spacing of these bands depends on the ratio of the wavelength to the slit width, the same ratio that determines how much diffraction occurs. A narrow slit produces widely spaced bands. A wide slit produces closely spaced bands, and the central bright band is always the widest and brightest, containing most of the energy that passes through the slit. This single slit diffraction pattern is visible to the naked eye under the right conditions. Hold two fingers very close together, leaving a tiny slit between them, and look through the slit at a distant light source. You may see faint bands of light flanking the main bright strip. Those bands are the diffraction pattern, produced by the interference of wavelets from different parts of the slit between your fingers. The light is bending, spreading, and interfering with itself, all because the slit is small enough for its wavelength to matter. When you combine diffraction with the double-slit setup that Young used, you get a pattern that is even richer. The two-slit interference pattern, with its regular bright and dark bands, is modulated by the single-slit diffraction pattern from each individual slit. The result is a series of interference fringes enclosed within a diffraction envelope, a pattern within a pattern, each governed by its own set of geometric relationships. The interference pattern depends on the distance between the two slits. The diffraction pattern depends on the width of each slit. Together, they create a composite pattern that encodes both pieces of information, readable by anyone who knows the physics. Diffraction and interference are not separate phenomena. They are both consequences of the wave nature of the disturbance, both arising from the fact that waves have wavelength and phase, both governed by the principle of superposition. Diffraction is what happens when part of a wavefront is blocked and the remaining parts spread and interfere. Interference is what happens when two or more waves overlap, and their phases determine whether they reinforce or cancel.
They are two faces of the same underlying behavior, two ways of looking at the same fundamental property of waves, the ability of waves to add, to subtract, to combine, and to create patterns of presence and absence that no collection of particles could ever produce. And this brings us to one of the deepest consequences of diffraction, one that reaches far beyond sound passing through doorways or light passing through slits. Diffraction imposes a fundamental limit on our ability to see fine detail. Every optical instrument, every telescope, every microscope, every camera forms images by collecting light that has passed through an opening, the aperture of the lens. And because light is a wave, and because the aperture is finite, the light diffracts as it passes through. The image is never perfectly sharp.
Every point source of light, every star viewed through a telescope, every molecule viewed through a microscope, is not imaged as a perfect point, but as a tiny diffraction pattern, a central bright dot surrounded by faint rings. The size of this diffraction pattern depends on the ratio of the wavelength of light to the diameter of the aperture. A larger aperture produces a smaller diffraction pattern, and therefore a sharper image. A smaller aperture produces a larger diffraction pattern and a blurrier image. This is why large telescopes can see finer details than small ones, not because they gather more light, though they do, but because their larger apertures produce smaller diffraction patterns and therefore higher resolution. And there is an absolute limit. No matter how perfect the optics, no matter how carefully the lens is ground, the diffraction pattern cannot be eliminated. It is a fundamental consequence of the wave nature of light.
Two stars that are very close together in the sky produce overlapping diffraction patterns. And if they are close enough, their patterns merge into a single blob, and the telescope cannot tell them apart. This is called the diffraction limit, or the Rayleigh criterion, and it sets the ultimate boundary on the resolving power of any optical system. To see finer detail, you need either a larger aperture or a shorter wavelength. This is why electron microscopes can see much finer structures than optical microscopes. They use electrons, which behave as waves with wavelengths thousands of times shorter than visible light, and therefore produce much smaller diffraction patterns. Diffraction is also why the sky is not simply bright where the sun is and dark everywhere else. Sunlight passing through the atmosphere is scattered by air molecules, and this scattering is a form of diffraction, bending the light in all directions.
The shorter wavelengths, the blues and violets, are scattered more than the longer wavelengths, the reds and oranges, because their wavelengths are closer in size to the air molecules doing the scattering. This is why the sky is blue. The blue light from the sun is being diffracted in all directions by the atmosphere, reaching your eyes from all over the sky, while the longer red wavelengths pass through more directly. At sunset, when the sunlight must pass through a much thicker layer of atmosphere, even more of the blue light is scattered away, and the remaining light that reaches your eyes is dominated by the reds and oranges. The colors of the sky, every sunrise and every sunset you have ever admired, are ultimately produced by the diffraction of light waves by particles in the atmosphere. So diffraction is not just a laboratory curiosity. It is the reason you hear around corners, the reason AM radio reaches farther than FM, the reason telescopes cannot magnify indefinitely,
the reason the sky is blue and sunsets are red, the reason microscopes have limits, and why physicists invented electron microscopy to push beyond those limits. And it is, along with interference, one of the two great proofs that light, sound, and all the other phenomena we have discussed are fundamentally wave phenomena, governed by wavelength, frequency, phase, and the elegant mathematics of superposition. Waves do what particles cannot. They interfere, they diffract, they combine and cancel. They spread through openings and bend around obstacles. They carry energy without carrying matter. They connect distant parts of the universe through traveling patterns of oscillation. And they do all of this because of a few simple properties. A restoring force that creates oscillation, a medium or a field that passes the oscillation from one point to the next, and a phase that keeps track of where each point is in its cycle. We have travelled a long way from the leaf on the pond, from the raindrop and the ripple, and the duck that bobs up and down. But the thread that connects all of these ideas is the same question we started with. The question that has deepened with every chapter, that has become more mysterious even as we have understood more. What is moving? When a wave crosses a room, or an ocean, or the emptiness of space, what is it that actually makes the trip? We are ready now to face that question one last time. We have followed waves through water, through air, through metal, and through the empty vacuum of space. We have seen that water waves carry energy across oceans without carrying water. That sound waves carry voices across rooms without carrying air. That light waves carry warmth and colour across the cosmos without carrying any material substance at all. At every step, we have encountered the same strange fact. The energy arrives, the pattern arrives, but nothing you could hold in your hand, nothing you could weigh on a scale, makes the journey. And now, having spent all this time with waves, having learned their language and watched their behaviour, we are in a position to answer the question we started with, or at least to arrive at an answer that is honest about its own depth. What is moving when a wave moves? A pattern, a relationship, a coordination among oscillations. That might sound like a dodge, like an answer that avoids the question by retreating into abstraction. But it is not an abstraction. It is something profoundly real. The pattern of a wave, the organized sequence of crests and troughs, the rhythmic alternation of compression and rarefaction, the oscillating rise and fall of electric and magnetic fields. These are not imaginary constructs. They are physical realities with physical consequences. They carry energy. They exert forces. They can heat your skin, shatter glass, knock down buildings, and transmit every word of every conversation you have ever had. The pattern is real. The pattern is physical. And the pattern moves, even when the stuff it is made from does not. This is a genuinely new kind of thing. In everyday life, we are accustomed to two categories: stuff and nothing. There are objects made of matter, and there is empty space between them. But waves do not fit neatly into either category. A wave is not an object. You cannot pick up a sound wave. You cannot put a ripple in a jar. You cannot weigh a beam of light. But a wave is also not nothing. It carries energy. It carries information. It produces measurable, observable, undeniable effects. A wave is a third kind of thing. Not matter, not emptiness, but a pattern of activity that moves through matter or through fields, carrying energy from one place to another. It is a process, not a substance, a verb, not a noun, a doing, not a being. and it is one of the most fundamental categories of existence in the universe. Almost everything in physics, when you dig deep enough, turns out to involve waves. Sound is a wave. Light is a wave. Heat radiates as a wave. Radio, television, Wi-Fi, Bluetooth, GPS, radar, all waves. The electrons in your computer's processor are described by wave functions. The protons and neutrons in every atom are bound by fields that propagate as waves. The gravitational influence of the Sun, which keeps the Earth in orbit, can be described in terms of gravitational waves that ripple through the fabric of space-time. Even the cosmic microwave background, the faint radiation left over from the Big Bang, the oldest light in the universe, is a wave, a pattern of electromagnetic oscillation that has been traveling for nearly 14 billion years and is still arriving at every point in the cosmos right now, including the room where you are lying.
And all of these waves, every single one, obey the same basic principles we have explored tonight. They all have wavelength and frequency and amplitude. They all travel at speeds determined by the properties of the medium or field through which they propagate. They all obey the equation V equals lambda times F. They all carry energy proportional to the square of their amplitude. They all exhibit interference, constructive and destructive, when two or more waves overlap. They all exhibit diffraction, bending and spreading when they encounter obstacles or pass through openings. And they all carry energy from one place to another without carrying any material substance along for the ride. The universality of this behavior is staggering. The same mathematics that describes the ripples on a pond also describes the oscillation of a plucked guitar string. The same equations that govern the spreading of sound through a concert hall also govern the propagation of seismic waves through the Earth's crust. The same interference principles that explain the colors on a soap bubble also explain the operation of anti-reflective coatings on camera lenses, the precision of atomic clocks, and the detection of gravitational waves by the LIGO observatory, which measured the stretching of 4-kilometer-long laser beams by amounts smaller than 1,000th of the diameter of a proton. All of these things, from the bubble to the observatory, are applications of the same small handful of ideas about how waves behave. There is something deeply satisfying about this. The universe is complicated. The variety of phenomena we observe, from the crash of ocean waves to the glow of distant stars, from the sound of a human voice to the structure of an atom, seems overwhelming, endlessly diverse, impossibly varied. And yet, underneath all of that diversity, there is a unity, a set of simple principles that appear again and again, at every scale, in every context, governing the behavior of every wave the universe has ever produced. This unity was one of the great surprises of 19th and 20th century physics. When Maxwell showed that light was an electromagnetic wave, he unified optics with electricity and magnetism, three fields that had previously seemed unrelated. When quantum mechanics revealed that electrons and all other particles behave as waves, it unified the physics of matter with the physics of waves, showing that the distinction between particles and waves was far less clear than anyone had imagined. When Einstein predicted gravitational waves, ripples in the fabric of space-time itself, he extended wave physics into the domain of gravity, the most universal force in nature.
And when those gravitational waves were finally detected by LIGO in 2015, a century after Einstein's prediction, the signal they recorded, the tiny stretching and squeezing of space itself, was analyzed using the very same mathematical tools: Fourier transforms, frequency analysis, phase measurement, that physicists had been using for centuries to study sound waves and water waves and light waves. The tools developed to understand the ripples on a pond turned out to be exactly the tools needed to decode the whisper of two black holes colliding a billion light-years away. French captures this idea beautifully in his book. He begins with the simplest possible system, a mass on a spring, and shows how the mathematics of that system, the differential equations, the solutions, the concepts of frequency and amplitude and phase, carry over, almost unchanged, to every wave phenomenon in the universe. The spring is the gateway.
The mathematics of a mass bouncing on a spring is the seed from which the entire physics of waves grows. And the reason is that the physical situation keeps repeating. Something is displaced, a restoring force pulls it back. The system overshoots, an oscillation begins. Whether the something is a mass on a spring, a molecule of air, a column of water, or the electric field in empty space, the mathematical structure is the same, and the solutions are the same, and the behaviors, interference, diffraction, resonance, standing waves, all follow as inevitable consequences. A disturbance occurs, a restoring force acts. The system overshoots its equilibrium, an oscillation begins. That oscillation passes to neighboring points in the medium or field. A wave propagates. The wave carries energy without carrying matter. It has a wavelength, a frequency, an amplitude, a phase. When it meets another wave, their phases determine whether they reinforce or cancel.
When it encounters an obstacle or an opening, it bends and spreads, its behavior determined by the ratio of its wavelength to the size of the obstacle. And through all of this, the pattern moves, the energy moves, but the medium stays where it is. This is the physics of waves. And it is, in a quiet way, the physics of connection. Because waves are what link distant parts of the universe to each other. They are how the sun warms the earth, how a friend's voice reaches your ear, how a radio station reaches your car, how a star that burned out 10,000 years ago can still be seen in the night sky. Waves are the universe's way of reaching out, of transmitting energy and information across distances that no material object could ever cross. And they do it all without moving anything. Think about what that means for a moment.
Think about the fact that right now, in the room where you are lying, you are receiving information and energy from sources all around you, near and far, seen and unseen. The light from your screen, the warmth of the air, the faint, imperceptible signals of radio and Wi-Fi and cellular data, the cosmic microwave background, the gravitational waves from colliding black holes in distant galaxies, stretching and squeezing the space around you by amounts too small to measure with anything but the most sensitive instruments ever built. All of these are waves. All of them are reaching you right now. All of them are carrying energy to the room where you rest. And none of them have brought any matter with them. The universe is whispering to you from all directions, in frequencies too low and too high for your ears, in wavelengths too long and too short for your eyes, in oscillations too gentle for any of your senses. But the whispers are there. The waves are there. They pass through you and around you, and through the walls and through the earth and onward, into the space beyond, carrying their patterns forward, endlessly, patiently, at speeds ranging from the languid pace of ocean swells to the absolute cosmic limit of 300 million meters per second. And every one of them started with a nudge, a disturbance, something pushed slightly out of place, a molecule jostled, a field perturbed, a tiny, local, unremarkable event that set off a chain of oscillations that propagated outward, carrying energy and information and pattern, connecting one part of the universe to another, across distances and through barriers and over time. The photons that warm your skin began as nuclear reactions in the core of a star. The sound waves that carry a loved one's voice began as vibrations in a pair of vocal cords.
The gravitational waves that stretch and squeeze the space around you began as the collision of objects so massive and so distant that human language barely has words for them. And yet, despite these vastly different origins, every one of these waves obeys the same handful of principles: wavelength, frequency, amplitude, phase, superposition, diffraction. The same language, the same logic, from a whisper to a quasar. Waves are how the universe stays in touch with itself. And that is, when you think about it, a remarkable thing. So here you are, lying in the quiet, surrounded by waves. The sound of my voice, if you are still listening, is a longitudinal wave in the air, a pattern of compression and rarefaction that was created by the vibration of a speaker cone or a pair of headphones and has traveled through the air to reach your ears.
The pattern of those vibrations is being decoded by your brain into words and ideas and images, but the air molecules that carry them are the same air molecules that were in the room before I started speaking. They have not come from anywhere. They have simply passed the pattern along, neighbor to neighbor, a chain of nudges that began at the speaker and ended at your eardrum. If you can see a light source, the light reaching your eyes is an electromagnetic wave, a transverse oscillation of electric and magnetic fields, traveling at 300 million meters per second. The photons that carry this light are not particles of the light source that have traveled to your eye. They are excitations in the electromagnetic field, patterns born at the source and propagated through space at the speed of light. The energy arrives, the pattern arrives. The field itself was already there, everywhere, waiting to carry the wave.
And beneath all of these, beneath every wave you can detect, and 1 billion you cannot, the atoms in your body are quietly obeying the same physics. Every electron in every atom is described by a wave function, a mathematical wave that determines where the electron is likely to be found if you look for it. The very structure of matter, the arrangement of electrons around nuclei, the shapes of molecules, the properties of materials, all of these arise from the wave nature of the particles that make up everything you see and touch and feel. You are, in a very real sense, made of waves. Patterns of probability, standing waves of quantum fields, oscillations so fast and so small that they are beyond the reach of any human sense, yet so fundamental that without them, matter itself would not hold together. The universe began, as far as we can tell, with a disturbance, an enormously energetic fluctuation in the quantum fields that fill all of space.
That disturbance set off oscillations that propagated outward, carrying energy, creating structure, evolving over billions of years into stars and galaxies and planets, and eventually into you. The cosmic microwave background, that faint, cold radiation that fills every corner of the universe, is the echo of that original disturbance, the remnant of the first waves, stretched by the expansion of space from gamma rays to microwaves over the course of 14 billion years. Those waves are still arriving, still reaching every point in the cosmos, still carrying the fingerprint of the universe's birth. So when you ask, what is moving when a wave moves? The answer is something very old and very deep. A pattern is moving. A relationship is moving. A connection between one place and another, sustained by the simple willingness of each tiny part of the universe
to oscillate in response to its neighbors, and in doing so, to pass along something. Energy, information, a message, without ever leaving home. And that is, perhaps, the most beautiful thing about waves. They are the universe's proof that you do not need to carry something physically from one place to another in order to connect those places. You do not need a pipeline, or a bridge, or a vehicle. You need only a pattern, a rhythm, a coordinated sequence of tiny motions, and the energy flows, and the information flows, and the connection is made. You are surrounded by these connections right now. They are passing through the walls, through the floor, through the air, through your body. They are carrying the warmth of distant fires, the light of distant stars, the voices of people you love, the data that lets you access the accumulated knowledge of your entire civilization from a device in your pocket. And every single one of them is a wave, a pattern that moves while the world stays still. Let that thought settle gently in your mind as you rest. The universe is full of motion, but most of that motion goes nowhere. It oscillates, it vibrates, it hums. And in that humming, it carries everything that matters from one place to another, without ever rearranging the fabric of the world. The air in the room is still. The light will fade when you close your eyes. The waves will continue, as they always do, carrying their patterns quietly through the dark. They have been doing this for 14 billion years. They will continue long after you drift off to sleep. And right now, in this moment, you do not need to track them, or measure them, or understand them any further. You have followed them far enough for one evening. From the raindrop on the pond to the electromagnetic field in the vacuum of space. From the nudge to the oscillation, to the wave, to the interference pattern, to the diffraction of light through the atmosphere that gives you the colors of the sky. The waves will still be here in the morning. For now, just rest. Let the oscillations slow. Let the amplitude of your thoughts grow smaller and smaller, gently approaching zero. Let the frequency of your breathing drop, each cycle longer and more relaxed than the last. You are a pattern too, a beautiful, temporary, astonishingly complex pattern of waves and fields and oscillations. Resting now, in the quiet, surrounded by the gentlest motions in the universe. And they will carry you, as they carry everything, softly and patiently, into sleep.